These astonishingly beautiful images are rocks. They've been sliced to half the width of a hair, and now they're viewed under a polarizing microscope. Each vibrant spot of colour corresponds to an individual crystal, amongst them bright and blocky olivines and pyroxenes, and also paler stripy feldspars, and occasionally there are little dark dots, spinels. They originate deep within the earth when physical conditions allow hot mantle rocks to melt. This molten rock is often referred to as magma. When volcanoes erupt, they bring up some of the crystals that were made at depth, and as these cool on the surface, they make a type of igneous rock. We're interested in the Earth's mantle, which stretches from depths of about 30 kilometres beneath our feet to about depths of 3,000 kilometres or so. Now, why is this an interesting place to look at? It's a very dynamic environment. There are strong fluid stirring motions that occur within the Earth's mantle, and these motions, even though they're really rather slow on a human timescale, they actually drive a lot of the forces that end up causing things like earthquakes and driving volcanic eruptions ultimately. Along with volcanic eruptions comes a supply, a cocktail of chemicals that are really important in regulating the composition of the Earth's atmosphere, the Earth's oceans, and this of course is what makes the Earth a habitable planet. But of course the problem with the mantle is that it's very difficult to observe. It's deep beneath our feet and it's very hard to get access to. So what we have to use are more indirect methods in order to study the deep interior of the Earth. These might be things like looking at seismology, seismic waves that are produced during earthquakes, or alternatively, you can use the composition of volcanic rocks that get made at depth to understand how the mantle works. Some of the most useful rocks for studying the mantle are found in volcanic islands in the deep oceans. And of course, it's very hard to go and collect samples from those sort of locations. Very labour intensive, very expensive activity. So if we want to do this sort of research rapidly, then what we're lucky enough to be able to do is to use a large collection of samples that is available to us in the Cambridge University Sedgwick Museum of Earth Sciences. This collection was started in the 1800s and has been built up over the last couple of centuries to be a very useful research tool. Today, as well as containing 160,000 rock specimens, there are also 250,000 rock slices that are thin enough to let light through. Drawer upon drawer is filled with samples from ocean island chains such as Hawaii, Samoa, Tristan da Cunha, Pitcairn and the Marquesas. Many of the samples were collected by Alfred Harker, one of the early curators of the museum. He was one of the early pioneers of the use of thin sections of rock to understand geological processes. Where once Harker would have used an optical microscope to look for distinctive crystals in the rock specimens, now we're able to use an electron probe, to use electron beams to examine the composition of crystals to look for traces of metals such as magnesium, nickel, iron, manganese and so on within certain crystals. The collection presents a marvellous opportunity for understanding how Earth's mantle works. Harker must have been a visionary to put together such a collection of rocks, because he must have understood that in future generations people would be able, as technology moved on, to be able to come back and revisit those sample collections and to realise the true potential of that collection for understanding the deep Earth.